Welcome back, everyone. In this lecture, we're going to discuss one of the most critical components of understanding k-means clustering, which is choosing a k-value. Recall our previous considerations, which were how do we actually choose a reasonable value for k number of clusters, and once we get some sort of k-value, is there really any way we can evaluate how good this current k-value is at determining clusters? So at the heart of it, how can we actually measure goodness of fit? For example, here we have 3 clusters, but how do we actually know how well these clusters are performing? Because this is an unsupervised learning problem, meaning we have unlabeled data. So we have no y label to compare to see how correct we are. So what we're going to do instead is we could measure the sum of the distances from points to cluster centers. And what we can actually do is punish distances that are really far away by saying the sum of the squared distances, or SSD, which we'll discover later on. And that's kind of similar to the idea of root mean squared error or mean squared error inside that root mean squared error, where you're using that square to really punish points that are far away from their cluster center. So here again, what we're going to end up doing is once we've decided on a k-value and we fit the algorithm, we're going to measure the distance from the point that now has a cluster assignment to the actual center of the cluster. So let's imagine a simple example starting with k is equal to 2. What we're going to do is for all of these points, for example, starting with the red points, we measure the sum of the squared distances from points to the cluster center. So for the red points, we have 3 points there. We're going to measure each of those to the cluster center, that is the upside down triangle in this example, and then we're going to measure that, and we're actually going to sum them up once we've actually squared them. And so we have some sort of measurement for how tightly packed that cluster is. And in theory, if it's a good cluster, you should have some sort of tightness to that packing. And then on the right hand side, we have the same thing. The green cluster, we're going to measure those distances, square them, and then sum them all up. And the better the fit for the cluster, the lower that value should be. However, there is a trade-off eventually. So what we're going to end up doing is let's try fitting an entirely new k-means model with k plus 1. So we go from k is equal to 2 to k is equal to 3. Now what happens? Well, again, we're going to measure that sum of the squared distance, or SSD, to the center for each of those points. And notice, pretty much by default, it should always be going down as you go further and further higher k values. Because what's going to happen is as you actually go to k, once it's equal to the number of points, SSD would go to 0. So why is that? Well, we can see here that I have 7 total points. And let's imagine I set k equal to 7. So for 7 points to find 7 clusters, what's going to happen is you're going to have a cluster for each point. So the distance from the cluster center to the point itself, which is essentially the same thing as that cluster center, would be 0. However, we just know intuitively this is not the actual solution we're looking for. So keep in mind, we're not actually trying to minimize the sum of the squared distance to the cluster center. Instead, we're using it as a measurement tool. So let's think intuitively, what are we actually trying to achieve? We want to actually keep track of this sum of squared distance value for a range of different k values. And then what we're really looking for is once we start hitting a k value where the rate of reduction in SSD begins to decline. And this signifies that adding an extra cluster is not obtaining enough clarity of cluster separation to justify increasing k. And I think we can visualize this further by checking this out as an elbow method. Keep in mind, don't get too confused with k nearest neighbors, which also operates on an elbow method. But the idea is kind of similar in the sense that you're looking for a point where your reduction rate is starting to get lower. So again, we're going to track where that decrease in SSD begins to flatten out compared to increasing k values. We don't want to minimize SSD to 0 because technically we know we can easily do that by setting k equal to the number of points. So instead, we want to look for that magic moment, so to speak, where adding in another k cluster is not really revealing more information about the data set. So we'll start off with k is equal to 2, and then you track these measurements, and you can actually then plot them out. And so on the x-axis over on the right, we have the actual value of k, and then we have the SSD for k is equal to 2. Then we're going to increase the k again and measure SSD. So for k is equal to 3, notice the SSD is going down, and it should pretty much always be going down for the most part as you increase the clusters, and eventually it'll just level out at 0. So you keep doing this, and now here you can see I have 4 clusters, but notice we're starting to get some cluster centers that are right on top of the point. So we're starting to level off. And you repeat this process for some set number of k values. You can pretty much go from k is equal to 2 all the way to k number of points, but for really large data sets, that wouldn't really make sense. You don't want to do 40,000 clusters for 40,000 points, especially because you have to recalculate and refit an entire k-means model for each of the points on the right-hand chart. So eventually what you're going to see is a continuous decline. And here, this is the chart we're actually going to code in just a little bit, where I'm measuring the sum of the squared distances for any particular k values. And the decline in the sum of squared distances from 2 to 3 is about the same as the decline from k is equal to 3 to 4. But you can see that rate is starting to decrease as we go from 4 to 5. So it's starting to get a little shallower. But you could make the argument that it's continuing more or less linearly. So you could push out the k value to something much higher. And if we were to do that, you then start to see those elbow points. And keep in mind, there's no 100% correct answer here. So what you could say is, here you have this elbow point at somewhere between k is equal to 5 and k is equal to 10, where increasing that next cluster is reducing SSD by a tiny amount. So that's probably a good cutoff point right before it to choose k number of clusters. But notice here, there's a wide variety of points that could be reasonable assumptions of where you would want to have a k cutoff, which means there's probably different ways to actually cluster these variety of data points in a way that makes sense. So if you have a really large data set on bank marketing clients, maybe you just want to separate them out into 3 groups, or maybe you want to separate them out into 25 groups. And those could be different clusterings or groupings that both make sense. Here we can end up looking for those elbow points and see where does it make sense to maybe do a cutoff where we're not actually decreasing SSD that much anymore by adding in a new cluster, and then start exploring that. And then that's where you could do the correlation with the features and see and try to understand based off your domain experience what these clusters are actually representing. Always keep in mind that because this is unsupervised, it's not really perfect. There's no 100% correct answer. This is where the art meets the science. So these points are strong indicators that increasing k further is no longer justified, as it's not really revealing more signal. You can also measure out this change in SSD in a bar plot. So we're going to explore this further with code by heading over to Jupyter Notebook. Alright, here I am where we left off last time. Recall that previously we checked out the correlation of features to the actual cluster labels. Now this actual plot and information tells you what features are being considered for the actual cluster groupings created by k-means. However, it doesn't actually inform you whether or not this k value was reasonable. For that, we go to the elbow method we just discussed. We can do this quite easily with a for loop. We're going to say SSD is equal to a empty list. Then for k in some range, for example, I could say starting at k is equal to 2 to k is equal to 10, create a new model. So a new k-means model where n number of clusters is equal to k. So I'm going to create a new model for 2, k is equal to 3, k is equal to 4, and so on. And then I'm going to fit that model on the scaled x values. And let's go ahead and scroll, give ourselves a little more space here. And once that's fitted, I'm going to say SSD, that list I created there at the top of the loop, and I'm going to append the sum of the squared distances of samples to their closest cluster center, and that is actually within the model. It's called inertia underscore, and this is what scikit-learn decided to label that. But again, it's simply the sum of squared distances of a point to its assigned cluster center. Okay, so you go ahead and run that, let that loop run. If you choose a really large k value, such as k's all the way equal from 2 to 40. Keep in mind, you are refitting and recreating a new model for every single k, so a large loop could take a long time. Here we're just testing a few, so the loop is done. If I say SSD, I can see here the sum of squared distances, and you notice it should pretty much always be dropping, but at a certain point, you're not going to be dropping as fast. So we can see here, from k is equal to 2 to k is equal to 1, you're having a drop of almost 100,000. And then as you go from k is equal to 3 to 4, again, you're having a drop of roughly 100,000. But then notice now we're kind of shifting over significant digits, and now it's only going of a drop of 70,000. So is there a big difference between a drop of 100,000 to now only dropping about 70,000? It's kind of up for debate. And again, it's something that you wouldn't really know unless you have domain experience. Check out the clusters, compare it to the feature correlations you previously discussed here, and just start kind of diving deeper into the data and see what insights you can gain. This is never going to tell you a 100% correct answer. It's just another tool in your toolkit to try your best to figure out what a reasonable k value is. So we can actually then plot these out. So I can say plot on the x-axis range 2 to 10, and then SSD, and then what I can do here is just a special little code, O dash dash. And if you plot that out, it's going to show you here on the y-axis, that's the sum of squared distances, and then we have the k values. So the sum of squared distances at k2, then 3, then 4, 4, and so on. And you can see here where it starts flattening out. So in general, probably k is equal to 6 is a really good idea, because you can see here the actual dropping from k is equal to 6 to k is equal to 7 is a lot less than going from 2 to 3, 3 to 4, 4 to 5. So these are kind of in the 100,000 range. Maybe this one's about 70,000, also kind of between 170,000. But you can see the distance from going from k is equal to 6 to 7 is a lot less. And one quick way to do this is using pandas. You can say pd.series, pass in SSD. That quickly converts it into a series, and pandas has the ability to actually calculate differences from one row to its previous row. And you can do that simply by passing in .diff as a method call. And I'll actually do this on a new line so you can see them both. So you can say pd series and then SSD. And once that's created, you can say diff, and that's going to calculate the difference between this row and its previous row. So the difference between this row at 0 and this row at index 1 is equal to, we can see here, negative 99,000. So you're dropping here. So you're looking for, where am I not dropping that much anymore? And the transition happens from index 4 to index 5. Note that I'm saying index 4 to index 5 because technically these are not actually k values. You should recall that now these are the differences. So what do these rows actually represent here on pd series ssd.diff? That actually represents these kind of connecting lines between them, where you have 0 here with not applicable or not a number because there was nothing previous to compare it to. And then here at index 1, you have that difference. Index 2, index 3, index 4, index 5. So technically, if we're seeing a big drop at index 5, that's actually equal to k is equal to 6. So just keep that in mind, that the automatic indexing from pandas could make this a little confusing. So here we see that big drop at index 5. That's actually technically equal to k is equal to 6 for the corresponding value here. All right. So once you choose that correct value of k, it's not really correct, but it's kind of your best guess. What you can do is come back and then measure out what features are related to the clusters and try to gain some insights that way. Okay, I hope this helped you out in your understanding of the unsupervised learning process for k-means clustering. Coming up next, we're going to have a really interesting discussion on a very practical application of k-means for color quantization. I'll see you there.